Hello, everyone. My name is Hamid. I'm an assistant professor at Utah State University. Today, I'll present our paper, Enhancing Individual Fairness Through Propensity Score Matching. You can see the name of other authors of this paper here. Machine learning models are ubiquitous and they are used in various domains, such as manufacturing, healthcare, insurance, and so on. While their performance has been celebrated, it has been shown that machine learning models exhibit bias and discriminatory behavior. For example, in that case of that famous application that's determined if someone will commit a crime again, it has been shown that model is very discriminatory against African American. Given this has been lots of effort to improve fairness of machine learning model. There are two major notions of fairness. One is group fairness, another one is individual fairness. Group fairness is the machine learning model prediction for certain predicted group. For example, women in college admission are the same as the rest of the population. For example, they should have the same false positive rate. Individual fairness is based on a similar, a very simple idea, but very powerful. It says similar individuals should be treated similarly. For example, X and X prime are two individuals or two data points that we think they are similar, then the model basically should treat them similarly, essentially give the same prediction for these two data point individuals. However, individual fairness has three major issues. One is, where do we get the similarity? How we can determine similarity between individuals? Another challenge is how we can incorporate this notion of individual fairness in model training and optimization. Eventually, how we can evaluate individual fairness in an effective way. As I will mention later, the current metric that is used for evaluating individual fairness has some shortcomings. Before presenting our proposed framework, I would like just to present some notations and the problem definition. Suppose we have this database, a dataset X with n individuals. S is a sensitive attribute such as gender, race, and we have the unprotected group, which, for example, are males. And S0 is used for sensitive attribute of unprotected group. Similarly, we have S1, sensitive attribute for protected group, which is used, which is denoted by XP, for example, female. And Y is binary label. In this paper, we just focus on binary classification, and we have 0 or 1. 0 is for privileged class, for example, getting a loan or being admitted to a college, and 1 otherwise. In addition, we have this adjacency matching matrix that for I and J, the value is +1 if two individuals are matched similarly, 0 if these two individuals are matched dissimilarly, and -1 otherwise if they are not matched at all. I will explain how we can construct this adjacency that maintain the matching information. So given XP, X, N, and A, we want to learn a model F that's give us C, which is probability distribution over the binary labels, that is both predictive and also fair. Then how we can do this? This is an overall illustration of proposed method. We call it FairMatch. So given XP and XN, it consists of 3 distinct components. One is propensity score matching, and then one is fair triplet optimization and individual fairness evaluation. I will explain each component in more detail. So propensity score matching estimates the effect of a treatment or policy by accounting for covariates that predict receiving the treatment. For example, if the treatment is attending a private school, then given this, we have a treatment group, those who attend the private school, and we have a control group, those who attend public school. Then outcome of our interest would be students' achievement. Then propensity score says individuals in the same strata are compared to each other. So it does stratification. How? It uses this notion of propensity. So in this example, propensity of a student is a probability of success given a student's attributes. So, for example, a student's parents' income or level of education. Then this probability is between 0 and 1. Then the stratification is simple. Those who have a similar propensity, they are compared to each other, as you can see in this figure. So, okay, propensity score matching and fairness. We know individuals are social entities in a stratified society based on socioeconomic factors such as race, gender, and so on. Then we argue that fairness and social stratification are not disjoint and they are related to each other. Then how we can marry these two notions? We use this propensity score matching. So, but the setting is a little bit different than traditional propensity score matching. Here, the outcome is the sensitive value of a protected group. For example, here, female, being female or femaleness. Then the treatment group would be protected group, control group would be unprotected group, and propensity is this probability that we can see here. So given attribute of X without sensitive attributes, we exclude the sensitive attribute. What's the probability of the sensitive attribute? In this case, what's the probability of the sensitive attribute is equal to being female? Okay, we learned this for all individual. There are many options, but we use a simple logistic regression. Once we have this propensity scores, we do this matching procedure. For every individual in a protected group, we compare the difference of propensity against all those in unprotected group if this difference is less than some threshold alpha, which is a parameter to this procedure or function. Then we sort the result in ascending order. This sim here is candidate similar match. And we do this also for a candidate dissimilar match, which we just sort all those in unprotected group based on the difference in propensities for in a descending order. Then from this candidate, we pick up top K for those who are basically similar. AIJ is a +1 for these. And top K from the similar, AIJ is 0. So this is how we do the matching process using propensity. And given this, we also have this notion of triplets, which is X anchor, X positive, and X negative. X anchor is a member of is a member of protected group that is matched similarly with X positive, which is a member of unprotected group. The same X anchor or individual is matched dissimilarly with another member of unprotected group. If, for example, a female is matched similarly with a male, and the same female is matched dissimilarly with another male, where we get the similarly and dissimilarly matched using this procedure that I just described. Then how we can incorporate individual fairness, we use this fair triplet optimization. Suppose F is embedding from neural network, basically takes an input and gives us a representation of that input. Then we use this famous triplet loss. Triplet loss says the distance of X anchor from the positive should be larger than the distance of the anchor from the negative one. Basically, we have this pull and push factor. So these two should have a similar representation. So in Euclidean distance should be as close as possible, and this should be as far as possible. How this distance is compared to this distance, how large it should be, using this margin, which is a hyperparameter. So if the individual has a similar representation, probably the model also, the prediction would be very similar, yes. But this triplet loss just does the fairness optimization, but we expect from the model to also have high predictive power, high predictive performance. In terminology of this paper, we call it utility optimization. To do this, to have high predictive power, we also add cross entropy. Basically, we create another loss function for each element of the triplet loss. Eventually, we have this final loss function, which this lambda controls how much we focus on fairness optimization versus utility optimization. As I mentioned, the current metric that is used for individual fairness evaluation has some shortcoming. This metric is called consistency, which you can see here, 1 minus this formulation here. So Wij for two individual I and j, if they are similar, is 1, otherwise is 0. And these are the difference between the prediction for these two individuals, absolute distance. These are final model prediction. So if the product of these two is 0, then the consistency is high. If product of this other than 0, which is 1, the consistency will diminish. But it has one big shortcoming. Suppose for two individuals here, one female and one male, xi, xj, the probability of admission, for example, in college, is 0.48, for this one 0.42. And we apply some thresholds to get the xy hat and xj hat. The threshold, suppose, is 0.5. Then from this, the final predictions are for this one is 1, for this one is 0. So they are not treated similarly. If we plug in here, the consistency basically will decrease. But if we apply another threshold, suppose 0.53, then the final model predictions are the same, then means they are treated similarly. So the bottom line is this consistency is very sensitive to the threshold that we apply on probability distribution that we learned from probabilistic classifier, including neural network. How we can address this issue? Suppose Ci0 is a probability of class 0 for sample xi from model. Then we introduce this notion of beta similarly treated, which for two individual I and j is 1. If the difference between this probabilities, absolute distance, is smaller or equal to some beta, and if is 0 if this is larger than some beta, and -1 otherwise. -1 in the case that these two individuals are not matched in any possible way. So this is T here maintains or stored the treatment from the model, but we can also compare it with the actual treatment or non-truth treatment, which is from that propensity adjacency matrix. Then from this, we can create this nice confusion matrix, which we call it treatment confusion matrix. So if the model says similar and ground truth is similar, we have true positive. So in the same way, also we can have a false positive, false negative, true negative. And from this, we can have a false positive rate, true positive rate. We can easily calculate this, but we can also change beta in the range of 0 and 1 and get a UC, which we call it area under curve, which we call it a AUC fair. So this AUC fair, unlike consistency, is not sensitive to threshold that we apply on probability distribution. We did some experiment on 4 data sets and apply our method on these data sets. COMPASS is a famous data set in legal domain. Output is someone offender would reoffend. Sensitivity to race. Predicted group is African American. Census is another famous data set in this domain. And it's the income of more than 48,000 American individuals. The output is income larger than $50,000. Sensitivity with 6 and predicted group females. We also have this law, which is output is passing a bar exam, and sensitive attribute 6, protected group, again, females. And we have this student, which are mathematic grades of 2 Portuguese high school. So output is pass if the grade is larger than 10. Sensitive attributes is 6 and protected group are female. In terms of the fairness, you can see our model outperform some representative baseline. The fairness is actually quite high. This basic is the one without any notion of fairness at all. It's just a simple neural network. Also, here you can see performance comparison in terms of the utility, which the common AUC, area under the curve. We distinguish it from AUC fair by adding this AUC utility and also F1 score, which you can see our model is also outperform the baselines. It means the model is predictive and fair, so it doesn't sacrifice one in expense of another one. We did also some experiment to evaluate group fairness, although it was not our focus. Our model in general delivered acceptable level of group fairness as well. So we can conclude that this model is quite effective. And thank you very much. Please let me know if you have any question.